Right. Yeah, my camera is still playing up on this machine, so but at least you can hear me, so that's the most important
Yeah.
thing. I hope you can see the board. Um, so really up to you. I know you said forces in action or electricity, but seeing as we did some electricity the other time, it probably would
Yeah.
make balancing it out with a little bit of forces, I think.
Exactly, yeah.
Unless you've got some pressing questions on electricity that you want to ask one or two before we start off on forces. And yeah, do you have any particular pressing questions on electricity? Anything you're looking at recently you want to quickly?
I guess I think the main focus would probably have to be sort of tension, sort of turning, just basically the whole forces and action topic, maybe just the harder questions.
Okay.
So yeah,
Do you want to
so
start?
that
It really is just going to be a question of trying to go through some exam type questions here, isn't it?
yeah,
Because I mean, the concepts themselves we've already covered, but as we know, me and you know with this subject, it's not so much the concept, it's applying the concepts that's always the trickiest part. The concepts themselves are fairly straightforward per se. Right.
exactly.
So if I try and pull out a past paper, and let's see if we can, is this it? Can I draw from here? Let's see, Matt's made easy. Let's see if we can get one here from MME website. So probably, let's have a look here. What that paper have some good questions. Modeling, let's have a look here. Yeah, there's some good stuff in here. Okay, complete that. Yeah, there's some good stuff in here. Awesome. All right, okay, we're gonna go for this one then. I'm just gonna download this one. So this is the 2020 paper from Modeling Physics, and Conrad, well, I just get here. So here we go. And how's your break been otherwise so far, Conrad? While I'm going through this, how's it been just as a general catch up?
It's been quite good. I've just mostly been doing work preparing for my work experience as well.
Of course, the week coming up, isn't it? Yeah, different routine coming ahead. Yeah.
So I'm gonna have to fit in that and also coming back home and doing a full day of revision.
Yeah.
So it's going to be a very busy week.
It will be a
next
very
week.
busy week. It will be a
Yeah.
very busy week. But at least anyway, it will be balanced by the fact that you had a bit of a break, isn't it? So
That's true. Yeah.
exactly.
That's true.
But as they
But
say, you
yeah.
know, you buy the land, you buy the stones, you buy the meat, you buy the bones. There's always there's always something in there that that won't always be liked or too liked. Should we? Right. Okay. Super duper. So beginning of the current flip chart. Super. Right. Okay. So look at this paper here. All right. So I just pick a few general questions as we go along, isn't it, from the paper, which we know relate to forces. Okay, something like this. Okay, it's not so much forces, but that's energy. I think you'd be okay with that. Which pair of quantities of same SI base units? I want something that's a little bit more calculation intensive. What about this one? The tennis, the force, the ball, which statement is okay? Have I got number 3? Why not? Let's start warming up with number 3, shall we?
Yeah.
Let's warm up with number 3.
Would you say the ball has downwards acceleration?
Yeah, absolutely spot on. Well done, good.
Yeah.
Sometimes that catches students out. They think that, okay, it's at its maximum height, so no acceleration, but actually the acceleration is constant and it's
Yeah,
always
it's always.
absolutely spot.
Yeah.
Correct. Good. Okay, so nice and straightforward. This is some A-level stuff, year 13 stuff. Year 13 stuff. Don't worry about that. Again, not so much into forces. Year 13, leave that there. Right, number 8.
Would it be would it be B?
You're absolutely spot on. Well done. Excellent. Can you explain why?
Well, since the block is stationary,
Yeah,
there's no resultant force
excellent.
happening, and if I mean it's not A because you can see that the normal force and the force that's going down the ramp is sort of go in the same general direction, not really creating an equilibrium.
Okay.
Yeah, so I think it's B.
Okay, I see how you've thought about it. There's another additional way to also just to enhance your understanding when you're looking at these problems. The thing is, because it's in equilibrium, so the condition for equilibrium is that firstly, there is no turning effect at about any point. The total turning effect is 0. The second is that, sorry, the forces, of course, there must be 0 resultant force. So in addition to the condition of there being a 0 resultant forces, if a resultant force is 0, it means that the forces themselves, if joined tip to tail, yes, should form a closed triangle. At this level, let's just stick to a triangle. The shape can be any polygon, but at A level, generally, it's a triangle that they want you to be thinking about. So we know that if I join the tip of this arrow, the weight arrow, to the tail of this reaction force here, yes, and I also do the same by joining the tail of the third additional force. They should all form the closed polygon. Now, if I look at this here, if I just look at this, that's the weight there, that's the tip. It's joined to the tail of the normal. So there's nothing wrong with this bottom part so far here. All this is perfectly correct between these two forces. However, this is saying that friction is acting downwards. And if this block is on this ramp, there's no way friction will be acting that way. Friction will be acting, it will be at the point of slipping downwards. Does that make sense? In which case friction would be acting, friction would be acting upwards. So the arrow for friction must be pointing in that direction. And the only one that meets the criteria is B. So I've still got this, the two correct arrows here and the correct label for friction. Okay, so if we look at the others, they're all disqualified on the basis of, firstly, also they're not even pointing the same. They have to be in the same direction as the forces in the diagram. So these are not even in the same direction as the forces in the diagram. Excellent. Right. Not worried about that. Okay, can I have a look at number 10? Why not? Number 10.
So when mass, if I use the equation E equals half Fx, or extension.
Yeah, so half Fx, you say?
Yeah.
Yeah, okay, cool.
So F equals MA.
Now, okay, I see where you're coming. I see if you've thought of another equation here. Now, this here, this force here refers to the applied force.
Yeah.
The force that you've applied, was if the equation you're referring to, F equals to ma, this is Newton's law. And this F here is the resultant force. So this F in this equation is not the same as the F in this equation.
Okay. Right.
Okay.
Yeah.
So any ideas how you might, but there's another formula you can relate this force to. And I'll give you a bit of a hint.
Sure.
There's another formula you can relate this force to, based off Hooke's law.
I guess it would just be F equals K F over. So there's the F equals Kx. But
Correct, absolutely.
yeah.
That has to come in.
Yeah. Yeah. Into
Now, generally, this F, what is it generally? It says a spring is stretched by hanging on it a variable mass. So a little diagram wouldn't hurt to just try and understand the question. So you've got a little mass M. What's actually providing this F, this force F?
Would it be wouldn't it just be gravity?
Correct. And what would
Pushing
be
it down?
the value of that force then in terms of what's here?
9.8, or would you do
Or you just
minus?
leave it as a letter, wouldn't you? You would just
Yeah,
leave it
yeah,
as
or
a-
G.
Correct. And so you just say mg. That would be the
Yeah.
force. This is equal to F. Or in other words, the weight.
Yeah.
Okay. So now we're getting somewhere. So now you can see that we can rewrite this equation as mg, the force, is equal to kx.
Yeah.
So far, so good.
Yeah.
We can do the same thing here as well if we want to,
Yeah.
because we know that F is equal to
Kx.
kx.
Half kx squared.
And of course, if we want to, we can put this mg.
In the kx.
Yeah, can you proceed from there, do you reckon? Does that give you a bit of a...
Yeah. So yeah, if you just do E equals half mg squared, is that correct so far?
Half mgx squared, you say?
Not no, half mg squared, just the mg, because
Okay.
you replaced it with, or
Yeah, you could do it that way. Yeah, go on.
but the x is squared.
Absolutely.
Yeah, so would you just leave one?
Might be a
You'll
good
replace.
thing. It might be a good thing. So the other way we might try and do is if we rewrite this here, kx, and we can say E equals half kx. In place of the F, I've written kx multiplied by x. So this gives us half kx squared. Does that make sense there?
Yeah, yeah.
Okay, good. So instantly here, we know that k is a constant. So in terms of our relationship or proportionality, do you agree that the energy is directly proportional to the extension squared?
Yeah, yeah.
You can see that from this equation, yeah?
Yeah.
Very good. Now what we can say is, well, how is mass related to extension? Are they directly proportional? Are they inversely proportional? What might you say?
Wait, could you repeat that? I think the audio was a bit.
So the mass and the extension based off Hooke's law. What relationship does the mass have in relation to extension? Are they directly related?
Related? Could you say directly?
You're absolutely right, because if G is a constant, which is 9.81, and K is a spring constant, which is also a constant, well, then these two variables, these are the only variables, these two variables must be directly related as well.
Yeah.
So if energy is directly proportional to extension squared, and extension is directly proportional to mass, then what should the relationship be between energy and mass?
Would it be...
So now we're taking...
I know what you mean. It's just I'm trying to figure out if you have to...
Or the other way you can do it, just to help visualize it, Conrad, what we can do, another way we can do it. So you're okay with this stage here, right? Where we got to mg equals kx.
Oh, would it, because you'd have to do
here,
m squared.
Yeah, so we know that
E squared. Yeah.
is equal to half kx squared. Okay, so now
Yeah.
here you can see that x from this expression, x is equal to mg over k. Are you okay with that?
Yeah, I just thought because x, if you'd have to square x in order for it to be directly proportional to e. So if you square x, you also have to square m.
Correct. Absolutely.
So would it just be m squared, the m squared one?
Correct. Absolutely. Absolutely. And
Yeah.
that's, you're absolutely right. And that's why I was going down this route and saying, well, if you take x now, because we know x is equal to mg over k, so you're just going to have mg over k squared, because that's the x
Yeah.
there. And so you're going to see that the e is directly proportional to m squared. Yeah, that's another way of saying
Yeah.
we got there in the end. Excellent. Okay. Oscillator, simple harmonic motion, SHM. That's yeah. Okay. A little bit of materials, so not quite directly related as such. So we might pause that one. Kinetic theory. Right, here we go. Something with forces. Are there tensions in here? I'm hoping there are tensions. Tow bar. Hopefully there are tensions if they're talking tow bars. Tow bar.
No, I mean this one's fine. It doesn't have to be too. This
All right,
one
cool.
seems like a good one to go through.
Let's go for it then.
Let's move at constant speed. Would you mind moving it down? So
There we go.
thank you. Delete the body diagram. Cool. Constant. Yeah, would I just go from the tip of the frictional force and connect it to the normal contact?
So in this case here now, just be mindful. So here, you're not drawing
Oh right, I don't.
particular forces. You
Yeah.
yeah, imagining
Oh right, okay, yeah.
point mass, and you're simply showing the forces acting on it.
I see. All right, so I wouldn't have to connect anything to.
You wouldn't have to connect anything.
Oh,
Absolutely
okay.
correct. You're absolutely right. You wouldn't have to connect anything. So key term here to look out for, if unsure, is this
Yeah.
here.
All right.
Free body, there is no
Yeah.
connection of any forces. You're simply showing the forces acting on the body.
Okay, so would you draw the weight the same length as the normal contact force, just vertical downwards?
You wouldn't draw it the same length, actually. Yeah. If they're in the same plane, then yes,
yeah,
good, but not possible to do so in this case. But
yeah.
it simply says complete. It hasn't said whether this is to scale or not anyway.
Okay. So I just draw just normal.
Where you just draw a line, yeah, as long as it's
Yeah.
on that plane. Absolutely right.
Yeah.
Follow that dotted line. Correct. That's your weight. Good.
Yeah. And then I would do the would it be put? I don't know what force to call it. Would I just call it a pulling force or?
So in this case, there's a
Or
tow
just,
bar, and in a tow bar, this will be very much like a rope, there being a rope. So if this was a
yeah,
rope, what force would you say would be in the rope?
maybe tension
Correct.
or
Absolutely, it's tension,
yeah.
under tension, as this is being told. So what direction would it take?
Doesn't tension go both?
So where would you draw the tension force in this case?
I would go maybe up to the,
Any direction?
yeah, away from the dot.
Would
So pointing away from the.
would you say that would be acceptable?
Would it maybe be more to, would it be in line with the frictional?
You're absolutely spot on. And another way to think about a free body diagram is that you draw it directly on the body itself. There we go.
Yeah.
Weight, the same thing you're going to do. Weight, you're right, friction there. Yeah, and we can see that they are directly opposite. So it would have to be absolutely spot on in line with or opposite to the friction, correct? And so anything going that way, labeled as your tension. Okay, so that's the key thing here, because I've said labeled as well. Super. All right. Any other calculations? What do they want us to calculate? Okay, they've given us some information.
Just copy down some of the.
Yeah. So 10 degrees, constant speed, 120 meters, we're told, from A to B. Okay. Okay, it's interesting. I'm just as I'm reading this problem, I'm beginning to see almost where the examiner is trying to go with it, I think. Show that the component of the weight of the car acting down the slope is about 1,900 newtons. Component of the weight acting down the slope. So let's see here, what information have they given you to do so? Okay, yeah. They've given you the mass of the car.
What was that question?
So it says show that the component of the weight down the slope is about 1,900 newtons.
Yeah, component down the slope. Down. Yeah. So I just did 1,100 kilograms multiplied by G.
Yeah.
Which was I can't remember what it was, but then I just put that answer as answer sine 10 degrees.
Correct.
And I got roughly 1,873, and I'd round that up to 1,900.
Correct. Excellent. Well done. No problem. No problems there. You've got the full mark. Part C.
Frictional force acting on. If it's traveling at a constant speed, would it just be 300 newtons, right? If it's just.
So in other words,
no
the resultant force would be 0. So it's worth going to the picture again. Would the resultant force be 0? Sorry, would asking you to work out, calculate the total force. Now, the hint here is in the word calculate. They're giving you a hint. You're going to have to do a calculation.
Yeah.
It's not just going to be an inference. If they wanted you to simply state an answer that was going to be the same as this, you know what they would have said? The examiner is very helpful. but I've used the words
So,
state the force.
yeah.
That would have
Okay.
been a hint to say you don't need to calculate the answer staring at you in the face.
Yeah. Okay. Sure. Um,
Also, just think about the earlier parts that you've done. Oftentimes, there could be a connection to an earlier part, to an earlier calculation that you were doing.
yeah. Mm. Would you just do 1,900 minus 300, or would you add it?
Oh, very good.
Or
Very good.
yeah.
Very, very good. So let's just have a think then. Would we add? Would we subtract? What would take?
You'd is it add?
Yes. Why would we
Yeah.
add?
Just because it's going at a constant speed,
Right.
and you kind of have to sort of
So the component of
make up for
weight,
that.
the component of the weight surely will be acting. There'll be a component of the weight that's acting perpendicular to the slope, but also down along with the slope. And that's the one you calculated as WS.
Yeah.
So along the slope, there is equilibrium, meaning that the sum of these two forces, friction plus the component of the weight down, must equal the tension which is acting in that plane. And
Yeah.
that's we want to work out the work done by the tow bar. So we need to know the force, and that force will equal this plus that. Good. And what do you get for that?
Yeah. You just add it 2,200.
2,200. 2,200. Calculate the work done by the force provided by the tow bar as the car travels from A to B. As it goes from A to B.
Do you mind if I just read that question one more time? Just
Certainly.
see the
Go back over here. Go.
force provided by the tow bar. The car travels from A to B. So for this one,
Yeah.
would you resolve I would you wouldn't use the number 2200 for this calculation
Okay.
directly.
You
Would you
could use, well, you could use it.
like
Depends
well, I mean, I did 2200 sine
Yeah,
10 to
good.
get the vertical force.
Yeah. Now, would it be sine 10? Just think about it.
Sine 10.
So there's 2,200 in here.
Yeah.
Tension. Let's come over.
And I'm trying to find.
So there's 2,200. You're trying to find the work. Work is, what's the formula for work?
Force. What is it? Is it? Yeah, just force times displace.
Correct.
Displacement. Yeah.
So in other words, we always look at the force and the distance traveled in the direction of the force.
Yeah.
So if you know what the force is, and you know the distance traveled from A to B,
yeah,
this force multiplied by that distance A to B gives you the work done.
Because I did the vertical force, but used by the tow bar, and the vertical distance from A to B.
You can, but you've just created another extra question for yourself, because the reason why they led you to calculate B and C is so that you could do it much easier over here. That's the reason why they did it. But you can still do it that way, and we should see that it should still check out. There's no harm. So here we're saying we've got 2,200. Yeah. And we're going to have to work out then that component. So let's have a look here. So you'd have 10 degrees here. So it would be T multiplied by sine 10. T sine 10 times 120. So you can either do it like this.
Yeah, that's what I do.
Yeah. Or you can simply T times, well, what's this distance AB? That distance AB. If this is 10 degrees, so we know we've got the opposite over hypotenuse.
Yeah. Yeah, so
the opposite over hypotenuse to work out that distance. So sine 10 equals opposite is 120 over hypotenuse. So the hypotenuse would be equal to 120 over sine 10.
691
problem here as well. Yeah, okay. So then this would give us that would be this distance AB. So then you say T times 120 over sine 10 would give you the work done. Now, if you went your way as well, by the way, over here, I've just spotted an error that we've just made. You couldn't just say T sine 10, by the way, sorry, and I'll tell you why. Because now you need to find, if you're going to resolve it in that direction, T sine 10, you also need to take into consideration this weight now.
I see.
And then you'd also have to take into consideration the component of direction. So the problem becomes a lot more complicated.
Yeah. Okay.
So it's better to use that distance. Not to worry, but I just realized that I've just spotted that we've missed something there. You'd have to take that into consideration. Okay, good little question anyway. Let's have a go at something where things are connected and their tensions and pulleys are involved, and see how we get on with that. Let's just bring in this question very quickly, see if I can squeeze in and fit more here. Yeah, awesome. Let's do it like this. I think the other questions in this paper, by the way, just trying to see if there's any others worth looking at. Young's modulus, heater, no. Okay, projectiles, questions. That's A-level-ish stuff. A-level-ish Kepler's. Sorry, year 13 rather. No problem. Right. Here we go.
With the weight of B be 14.7 newtons.
Yeah. On. Oops. 14.7 newtons.
Would you just write that as 15, or would you just, since it's to one decimal
Well,
place?
actually, here things are being written to 3 sig figs,
Yeah.
and G has been taken to 9.81, in which case your answer should be
Yeah.
3 sig figs. Yeah,
Brilliant.
good.
Yeah.
Awesome. Next one down. Calculate the time taken for mass B. Oh, no, sorry. B part. All right.
Could you say for the I that the force of A is acting in the opposite direction as free fall, sort of, since it's on B, since A is sort of slowing down the acceleration.
And what you really want to talk about here is you want to mention that what do we have in this rope? There is tension.
Yeah.
And we know that the formula for acceleration is what? Resultant force equals mass times acceleration. So if this was falling freely and there was no tension, the resultant force on it would just be 1.5 times G if it was falling freely. However, now you've got a tension. So the resultant force is less. So now it's 1.5 G minus T. If it's falling downwards, it's 1.5 G minus T. Yeah?
Yeah.
So you're right. So you want to phrase that by saying that the resultant force due to the tension, acting on B, the resultant force would be less than it would be in free fall. Less than it would be in free fall.
Yeah.
Okay, calculate the time taken for mass B to fall 1.4 meters. So to just give you an idea of this is 3 marks.
Would it be one point I either got around 1.53 or 1.67. It was a weird one because I sort of didn't know how to
What was
I didn't know how to
which
treat
one
that.
did you go for directly? Okay. So let's just look at a few key things here. So they've said constant downwards acceleration. So as long as acceleration is constant, it means that we can think suvat.
Yeah.
So which equations can we start thinking of here? You've got, yeah.
Yeah, you could
Time
do
and distance.
t equals root 2a s plus u squared
Okay, I think you broke
minus
that. See, you've
u
changed the subject.
over
So is it this one you started off with?
yeah, and then I just rearrange.
Then you've rearranged. Okay. Now,
But I guess you don't really need
I
to
wouldn't have
since
normally
u
rearranged
is
at this stage. I'd leave it as it is. But it's all fair and good if you want to.
yeah, but you
So
can get rid of u and
we know what S is. We know what the
yeah,
initial velocity is. What's the initial velocity?
0.
Correct. So this term disappears.
So yeah, you
Absolutely right. And we know what the acceleration is. And what's the acceleration?
1.09.
Correct. So then the question now, or it now looks like 1.4 equals 2.5 times 1.09 times t squared.
Yeah.
Happy.
Yeah.
Good. So whatever half of 1.09 is, we divide. And if we take the square root, we should have that t is 1.6 seconds. If you take the square root there.
Yeah, that's what I got. Yeah.
That's what you got. Yeah, good.
Yeah.
Awesome. Excellent. Now for the next part, oops, still again involving a little bit of Suvat, or is it, sorry, just the last part. Okay.
Let's see. Would the velocity be about 1.3 or
1.3, a little bit over that should be.
oh wait,
So formula then, did you use v squared equals u
oh, wait.
squared plus 2as?
I mean, or could you just do the acceleration times the time?
This here?
Yeah. Oh, so it's 1.7.
You could alternatively do that. So that does
Yeah.
1.7.
Yeah, 1.7.
That's around the
Yeah.
range, and we'll get the mark for that. Okay.
Yeah.
Don't worry too much about this one here. You can work out again. This is just using Suvat. Let's try and have a look at something slightly different, maybe. There we go. So this here is for 4 marks.
would the resultant force would that be 35 newtons?
35, spot on, well done.
And the angle, let me just do that. Would the angle be 60 degrees?
16?
60.
60 degrees, 60
Yeah.
degrees, yes. Yeah, or about 59,
Yeah.
on about there, depending
Yeah,
on
yeah, 59. Yeah.
roundings there. Yeah, absolutely. So angle 59 degrees. Okay, well done. Good. Awesome. So that's all for 4 marks there. And the final part of this, which is just 2 marks, it's not really calculational, but why not just finish off all 6 marks. There we go. Right. State 2 factors that affect the magnitude of the drag force in this balloon.
Could you say the acceleration or the acceleration of the balloon?
Acceleration?
Yeah, or velocity. Yeah, I think just acceleration is fine. And
What would be
could you
a safer thing to say instead of acceleration?
maybe velocity?
Related to, absolutely, because drag force,
Yeah.
remember what I said?
Velocity squared, isn't it?
Correct, absolutely.
Yeah,
So you want to talk about velocity here.
it's probably safer, yeah. And would you also say maybe the surface area?
Absolutely, yes, surface area. Okay, we can talk about the shape of the balloon. There'll be so many things here: the texture, the temperature, the density of the gas in the balloon. All those things will affect the drag force. Good, and we have neatly then come to the end of our close. We've done a bit of an assortment of
very neatly
here.
Yeah, it's a very good.
A little bit of practice is better than none at all. So
exactly.
Demonstrated that you've been able to get some good marks on a good number of these questions. The multiple choice, of course, hang on, just anything to add, hang on. Yeah, the multiple choice, of course, just very importantly, remembering when we looked at that Hooke's law question, that F, importantly, is a different force. And then also when calculating work done, and just remembering that whenever you're doing these papers, oftentimes, if you've done something in a previous step, you might need to use it. So there's no harm in developing a little bit of a habit of asking yourself when you get to, especially the question that's going to have more marks. So there's 3 marks here. They've been building you up, going 1-1. The reason why they're doing this is to almost help you make it easy, because otherwise they could have easily simply asked you this question and just said, calculate the work done by the force from A to B. Not ask you this or that, and then they would have had to make this at least 6 marks. But because they've broken this down, they know you've got prior information that you can use on your 3 marker. So it's a general style of OCR physics papers. So if you can remember that, you will panic less when you see questions which are 3 marks and you kind of go, oh, I don't know how to go about it. Simply ask yourself, what did I do before that I'm going to have to use it somehow, somewhere? How could I possibly use it? Okay. Anything else that you add? yes, just remembering that, of course, you will see lots of symbols that are very similar in many formulas, like F equals to MA half FX. So just being
Yeah,
aware that at times they can mean different things. So
yeah.
but again, with experience, you begin to learn more of that. Anything else to add from here in terms of takeaway points on reflection? Yes, I'm glad. I think this can be a bit tricky, yeah, triangle
Mm.
forces, but I think with time again, you pick the right one. On another day, it would be good to do one maybe that is maybe not multiple choice, maybe long structured, which is more,
Yeah, definitely. Yeah,
yeah, would be worth your while. Good stuff. But yeah, all in all, I think a really good
really
session.
awesome.
Yeah. How did you
Yeah,
find?
that was really good. It was really good.
Awesome. Excellent. Righty. So have a great week ahead of you. It will be a case then that I probably don't see you until
Maybe the weekend or
I was thinking so.
such.
You just want to
Yeah,
keep me updated and send me a little message or a little text or something.
yeah.
And we just
Because yeah,
we'll work on that basis. I mean, we can provisionally set a provisional time, or in the week when
mm,
you've had a bit of a think as to which time would work best for you, drop me a line
yeah.
and we'll work
Oh,
from there.
yeah. I mean, because I finished my work experience, which is in central London, at 5:30, and it would maybe take me an hour and a bit to get home.
I was
So I don't know
thinking
how late you're willing to teach, but
Friday. So
just
if you're finishing about 5:30, so you'd be home, say
yeah,
7,
about 7, yeah.
which would mean if you really want to give yourself just to be on the safe side, you want to say starting about 7:30, then don't you?
Yeah, or I mean, as yeah,
Should
hopefully
we
earlier.
do
Yeah,
7:30 then? 7:30 to
we'll
8:30.
try 7:30. Yeah,
Yeah, okay, cool.
that
So
sounds
I'm just
good.
gonna
Yeah.
write that down here. So next lesson, Friday,
Mhm.
7:30
7:30.
p.m. to 8:30.
Awesome,
Good stuff. And let me know if there's anything
brilliant.
particular that you want to go through. But I think it's quite important that this what we're doing here is also just as important. We've covered the theory, but then we're going through exam questions together. This is a
Yeah,
very, very useful thing to do. Um, awesome. Good stuff. Have a lovely
awesome,
rest
brilliant.
of the week. Yes. And
Yeah.
working in central London, the hustle and the bustle.
Puzzle, yeah, exactly. It's gonna be lot.
It will be something to tick off the box once you've done it anyway.
It
You say,
will, yeah.
"Done it, got the badge,
So
and
tiring.
put it in the UCAS application now."
Yeah,
Right. So,
yeah. Oh gosh, it's gonna be absolutely horrible. But yeah, so
I know. Right. Enjoy it with a
exciting. Yeah.
smile. See you soon, yeah?
You too. You too. Have a
Cheers.
have a good day.
You too. Ta-da. Bye now.